Hello. Climate change in Europe drives not only extreme weather events, there are other threats, and those are infectious diseases that are sprawling with vectors across the continent. One of those is Lyme disease, also known as Lyme borreliosis. What links this disease and Earth observation? First, we look into a plot of the reported Lyme disease cases in Poland from the beginning of the century. We may observe a steady, near linear rise of detected cases, and after 2015 it accelerates. The slight drop from 2019 to 2020 is an effect of COVID-19 pandemics. Some cases were unreported, and COVID restrictions reduced people's mobility, what in effect reduced the probability of being bitten by a tick. That's why we see a decrease in cases here. But excluding this drop in the recent time, a similar rise of cases can be observed in all European countries, especially those with mild or cold climate. Why is that? Researchers propose that the warming climate and short, relatively warm winters may play a role here. That's why we focus our attention on the bioclimatic variables. We may observe those from the space, and with it, we can construct spatial and temporal models of Lyme disease infection risk. There are a few things detected from the orbit which are indirectly linked to Lyme disease. This link is through the tick's environment. We naturally know that arthropods can thrive in the scorching concrete landscape of the city. Ticks, which are a vector of Lyme borreliosis, prefer a wet and shady environment. It is even proven that hard-bodied ticks are frequent guests of the deciduous forests and meadows nearby, and what is no good for us, they tend to invade city parks and small green spaces. What is good is that we may observe vegetation from space and distinguish types of vegetation, ground humidity and landscape type. Those are important for ticks, their hosts, and human activity, which sums up to the probability of infection in a given area. Knowing the areas which are safer for ticks, we know where the risk of infection is higher for us. The model for infection risk assessment is not a simple one. It is divided into two parts. One part for the population at risk estimation, and the second, which is the species distribution model. The first model uses the geostatistical approach of Poisson kriging to transform county aggregate of a disease rate into population size blocks of the risk areas. In practice, it is a transformation that leads to the deconvolution of large areas to the small blocks, comparable with the remotely sensed pixels. The other models uses the general procedure of species distribution modeling. We use variables that correlate with the tick's occurrence to construct a probability map. Probabilities in this map are treated as weights for the final model of risk, which is used for the decision-making process. Here we see a transformation in action, from the country aggregates up to the Lyme disease infection risk map. The average size of a block in the first country level map is about 40 kilometers squared. The whole procedure generates a map of the size of population blocks, which is 3 kilometers squared. What is interesting and important here is that we can use three different approaches to tackle the problem of Lyme disease infections. We may focus on the ticks' occurrence and their habitats. We may put our efforts directly to the population at risk, or we can sum both approaches and try to find hotspots of infections which are close to the population at risk. This model is not ideal and it's under development. But from our side, it is a small effort to prepare Europe for the future, which can be more challenging for our citizens. At the same time, it could be more predictable and paradoxically safer with the help of remote sensing. Thank you, I'm Szymon Molinski, lead data scientist from Data Alliance Company.